back.
All right.
So our next presentation is in Berkeley, but probably in the hotel in Berkeley. I see you on the screen there, Joel, but you are feeling ill or something, so that's why you do this online.
Yep.
Anyway, I don't know if you see us. Do you see us or not? Or
yes, I do.
A little bit, okay. So if people have questions during the talk, you can try to sort of just ask, and if Joel doesn't hear it, I can in the microphone maybe repeat the question. But anyway, you will talk about contagions and hybrid phase transitions. The floor is yours.
All right, thank you. Yeah, great to be here. So I'm going to be talking about some work that I've done in the past. So this isn't incredibly recent work, but this is work that I've been doing and hope to get back to a certain amount to discussing complex contagions.
If you can tune up your volume, that would be nice, or maybe someone in the control room.
Okay, let me see what I can do. What microphone is it using? It's using this microphone.
It's good. It's good now. Maybe someone in the control room help us.
Okay, that could be. All right. So I'm going to be talking about some work that I did a little while ago, and I've been hoping to get back to kind of the regime of thinking about information spread. The reason being that I think that information spread is a really important thing, in particular misinformation spread and rumors and such. I think that both politically and, as we've now discovered, for healthcare, this is a really important issue to be thinking about. So let's talk a little bit about what I'm going to talk about. I'm going to talk about SIR disease, and I'm also going to talk about a similar model, basically a generalization in some sense of SIR models, the Watts threshold model. This was by Duncan Watts, who I believe was a PhD student of Steve Strogatz at one stage. Certainly they worked together. And I'm also going to discuss a model of random networks. You guys are familiar with configuration model networks, and some of you may be familiar with the fact that there are clustered networks that are of similar structure to configuration model networks, in that they have something like a tree-like behavior. So we can do some of the same analysis with a bit more effort, but we can do some of the same analysis that we can do for configuration model networks. I'm going to put all of the stuff you see there, the Watts threshold model, and these clustered random networks into a mathematical framework that lets me predict something about the dynamics of the Watts threshold model. And some interesting behaviors will emerge. So I'll talk about phase transitions and probably a few other things related to them. So let me start with just a review of a concept from dynamical systems, which are Cobweb diagrams. So in discrete dynamical systems, we often have this case where we have some point x, which depends on time, and it's given by some function of the next point is given by a function of the previous point. So we've got a discrete point. We go from x of 0, we find x1. We go to x1, we find x2. We go to x2, and we'll find x3, and we keep repeating that. And there's a fixed point of these maps. Now, Cobweb diagrams, I'm assuming some of you have seen this, but perhaps not all of you, particularly those of you who think more about statistics, are a way of doing this iteration in kind of a quick way. You start off at x0, you go to x1, and then instead of jumping over to x1 here and looking up, you just draw a horizontal line to this point, which is at x1. So this is the point on the line y equals x. And then you just go up, and then you go over to that line again. You go down, you go over to the line, and you keep going around. And you get something that, under certain circumstances, looks kind of like a spider web, hence the Cobweb name. There are some nice stability issues of this, namely, if you're very near the fixed point, which we'll call x tilde, So your x of t is till x is the fixed point plus a small value. Then we can do just a little bit of a Taylor series thing. We say x tilde plus epsilon of t plus 1. So that's your next, that's x of t plus 1, is your function of x of t. And I can do a Taylor's expansion. My leading order term gets me f of x tilde, but I've chosen that to be my fixed point right here. So I get x tilde plus the derivative, the local derivative times epsilon at the previous time. And so that means that epsilon of t plus 1 is this map where we got epsilon of t plus 1 is approximately a constant times epsilon of t. If that constant is less than 1, you're getting closer. If it's bigger than 1, you're getting farther away from the fixed point. So you learn about stability. And depending on the sign of it, you can also have it if that constant is negative. So like in this case, it's got a negative slope as you go across here. So the derivative is negative at that fixed point. You start, once you get close enough, you start oscillating from one side to the next each time you do the iteration. If the derivative is positive, but less than 1, you approach it, but you approach it kind of in a monotonic way. If the derivative is equal to 0, which I will talk a little bit about, a case like that, the approach can be very, very, very slow. All right. Now, let's talk about contagion. You guys are pretty familiar with this sort of thing. I can go around and I change the status of someone else. In fact, right now, perhaps if I were there, I would be changing the status of some of you guys through the fact that I maybe have a virus of some form. And this version sometimes referred to as a simple contagion. A single individual can cause you to change your status. In a rumor case, it might be that just hearing the rumor from one person is enough to make you believe the rumor. But there's another version where it's just that, you know what, I don't believe the rumor, particularly, maybe it comes from Greg, and I'm not convinced that, Greg's a particularly trustworthy thing. Now's the time to mention my brother's name is Greg, but no. But I might hear something from someone, and well, maybe it's plausible, but I'm not convinced. But I go to my social media and everybody's saying exactly the same thing. Well, then maybe I'm actually going to believe it. So you go here. The particular example I've chosen there. I don't know if you can read it, but an example from my life was, I heard one guy give a talk where he explained how some interactions of hailstones can cause charge to misbalance and charge from high in the clouds to the ground level, and that can cause lightning. And I was telling some people that, and they weren't really believing me. So they asked the guy who happened to be walking past, who was director of the Center for Nonlinear Studies, if he knew what caused lightning, and he said exactly the same thing. So they believed us. And then I asked him, who told you that? And his source was exactly the same. So they took it as kind of independent information, and therefore they believed it. You hear it from independent sources, it's credible. But, sometimes it's not really independent sources. And that, I think, is a really big potential issue in our society right now. You hear the information a few times, you think everybody's credible, but they're all getting it from the same place. So your kind of judgment is perhaps skewed. Okay, so I guess with this, I want to just get across this idea that there's a complex contagion where you could hear something from multiple places, and there are these simple contagions where it just takes a single where the change in status is due to a single interaction, whereas here the change of status is potentially due to multiple interactions. Okay, I want to set the stage a little bit more. Most of you guys are reasonably familiar with this idea. We've got a network, we've got susceptible individuals. They can become infected because of interactions with infected neighbors. And for me, when I'm going to use beta here, I'm thinking about this as a rate per edge, so per partnership. So if there's a partnership at rate beta, it causes this transitions to happen. And then all of these other ones have a potential rate of beta of causing transitions to happen, and one of them happens. And potentially at some later stage, somebody recovers. So the recovery happens, this person recovers with immunity. The Markovian model that I'm going to use, the fact that I say these things happen with rates beta and gamma, means that there's no reason to expect that this initial infection would recover any sooner than one of the other infections. So you can certainly convince yourself of this fact, but it's worth highlighting, just being aware in the back of your mind that our models make that assumption. And that may not be an accurate assumption all the time. In fact, it's probably not an accurate assumption, and it may lead to kind of some mistakes in how we think about the outcomes of our models. All right. And I want to kind of represent these transitions that can happen through a pair of directed graphs. There's two types of transitions that happen. There's the S to I transition, which happens because of somebody else. And there's the I to R transition, which happens purely because of things that are happening within myself. So I'm going to think I've got an IS pair that can become an II pair at rate beta, and an I individual can become an R individual at rate gamma. So we've got two kinds of transitions: the transitions that can be caused by one neighbor, the transitions that are caused by internal dynamics. And I can think about now, I can represent a system where there might be many kinds of transitions that can happen. And I can encode all the ones that can be caused by one neighbor in actually a directed graph, all the ones that can be caused by somebody's own status. So I could have another node E goes to I goes to R. I can have a directed graph that encodes all these sort of internal dynamics. And it turns out that if we have that framework, we can kind of build up a more general class of models. And for what it's worth, if you are interested in doing these more complicated sorts of transitions that can, or systems where there are more different states and people can change status because of the neighbors in different ways, I have software that can do that for a network. Okay. All right, so still I'm giving a little bit of introductory material here. I want to talk about the watch threshold model. So I'm going to slow down here because this is likely to be new for a lot of people. So it's like the SIR model, or more specifically, it's like the SI model. So think about it as SI. And I've got a susceptible individual who has a bunch of neighbors. That susceptible individual has associated with him a threshold, which I'll refer to as R sub U. So node U has a threshold R sub U. It might as well be an integer, positive integer or non-negative integer. And once this individual has at least that many infected neighbors, it will transition to infected. So for example, this node here has a threshold of 3, and once he or she has reached the value of 3 infected neighbors, there's a transition to infected. It's not immediately obvious that this is that there's time in this. Or more to the point, there's multiple ways that I can put time into it. But if you have kind of these rules that if I have at least 3 infected neighbors, I will eventually become infected. If we think about this threshold in that way, no matter how you put time into it, you'll get the same final state. And you can create a dynamic model in several different ways. One of them is to just say that once I reach my threshold, I have a rate at which I will transition to this state. There's multiple ways to put this in and create something dynamic. Often we're just focused on, when we study these models, on the final state, and I'm going to focus on that. Another way to put time in, which will be similar to what basically will correspond to things you'll see later, is basically at one time step, everybody who's at their threshold transitions to infected. And then once you've done that with everybody, you go through and now you look again. You cycle through again everybody who's now at their threshold and transition them to infected. And you just keep repeating that each time. At the start of the step, you figure out who has reached their threshold, and then those people will transition at the end of that step. I want to make one comment for an SIR model. It can be kind of interesting exactly how if you're careful about how you assign these thresholds, you can create the same final state as an SIR model. It's not as simple as saying the threshold's 1. You've got to assign a random set of values of these thresholds, but you can, if you choose them from the right distribution, you can create the final outcome of an SIR epidemic. So this is, in some sense, a generalization of the SIR model. And there are actually a lot of models out there that people use that can be considered as special cases of this. So let me stop here. I'll pause here and just see. I want to really make sure you guys understand this model before I move on. Are there any questions here?
Well, I can ask one question. So you haven't talked so much about the network. So there is an underlying network that is given to you, or?
Yeah, so I think about this as there is an underlying network. So think of a picture like this one. Perhaps this individual has a threshold of 1, and this individual has a threshold of 1. Then what would happen is you get, at the first step, this person becomes infected, stays infected. At the next step, this one becomes infected, stays infected. And if these people have a threshold that's 2 or more, is bigger than 2, if they have a threshold that is equal to 2, then at the next step, they would become infected. This one clearly has a threshold of bigger than 1, otherwise they would have become infected. And I do not have a recovery, but you would have this sort of a picture. And if these people have a threshold that's bigger than 2, we're done. Nothing more is going to happen. If one of them or either or both has a threshold equal to 2, they would become infected at the next step.
Thank you. Are there other questions about the model? No, it doesn't seem like it. So continue.
Okay. All right, cool.
So maybe one more question. Yep. So are these thresholds random or individual based? Or
there's various rules on how we can assign them. What I'm thinking of here is that I assign these thresholds randomly to each individual, and from some distribution. You could also do it where that is coming from a distribution that cares about my degree. So you could do it where if I have 100 contacts, I might be expected to have a different threshold than somebody who has 5 contacts. So often it's done when you reach some proportion of your neighborhood is infected. But here, what I'm thinking about is just there is some distribution that's out there, and we are going to use that distribution. We're going to choose for every single person, we'll choose a threshold from whatever that distribution is. Okay. All right. One way I can do this with time, I want to talk a little bit about one way I can do this with time. I can basically think about this as sort of a discrete time version, where what happens is if you're at your threshold, if you are an individual, you're susceptible, you have a threshold of 1, you get immediately mapped to an infected individual. This I, and you've got a new neighbor I that converts you to an infected individual. So if this is, you've got an infected neighbor who you haven't interacted with before, hasn't previously been infected, you have a threshold of 1, you become infected. Or you start off with a threshold that's bigger than 1, and as soon as you have an infected neighbor, you become somebody who has a threshold of 1 less, and we no longer let that neighbor affect you. And so we basically can build up a directed, we build up a network that consists of a whole bunch of edges that look like this. I to SR goes to I, SR minus 1, and we can kind of encode this. I am insisting that the edges only transmit once. Or another thing we could do is we could actually make this p below 1, and this would be sort of like, this would allow me to think about it as an SIR state. It would be possible to have something like this. That's another option I could do. I could include a recovered state where somebody stops influencing their neighbors and have something where that transition isn't guaranteed to happen. I'm going to stick to the SI kind of formulation, so I'm not going to have this transition happening. All right. For those of you who think about networks, there's a whole bunch of models that can be shown to be equivalent to it or special cases of it. And K-core percolation, there's something people call heterogeneous K-core. There's something there's more than one thing that people call bootstrap percolation. That caused me a lot of trouble when I was studying this question. There's something in the literature called the generalized epidemic process. You can make site percolation become a special case of this, and you can make bond percolation if you think about what the final component looks like of the final giant components, basically site percolation, bond percolation or actually the entire component distribution can come from this. All right. Now, this next one, I think a lot of you are aware of, but I think it's a nice demonstration. You guys know configuration model networks. You're probably aware of the fact that your friends have more friends than you do. You may even be aware that configuration model networks can help you explain why that's true. And so what I'm going to do here is I'm going to take a population where there are 3, everybody has either degree 3 or degree 1. And I start off I'm going to create it by giving each person either 3 or 1 stub. And I'm going to choose a random pair of stubs. I'm going to construct it, and we're going to build up a configuration model network. That's the model. But unfortunately, the numbers we have in that room don't look very large. But what I'd like you guys to do is each of you choose one of these nodes. Try to do it at random so you don't choose the same as somebody else. And we're going to look at a few images, and I'm going to ask you questions about your node, and you can raise your hand. So look at your node, choose it. I'm going to give them some stubs. If your node has degree 3, could you raise your hand? Okay. If your node has degree 1. All right. That looks kind of like about half and half. Oddly, people seem to be really bad random number generators, and very often that doesn't happen. But it's about half and half, and that's what should happen. Half of these nodes have degree 3, half of them have degree 1. Now, in the next image, I'm going to wire this network up, and I want you're going to choose one of the edges coming from your node and look at the neighbor along that edge. And so same node, choose one of the neighbors at random. Now, if your neighbor has degree 3, can you raise your hand? Okay, and if the neighbor has degree 1. Okay, we should have gotten about 3 times as many to have degree 3 as 1. And the reason for that is because the probability your neighbor has degree K is proportional to K. This is, for an infectious disease, this is incredibly important because those high degree people, they get infected sooner, and then they transmit to more people. This is particularly for sexual networks. This is a big deal. I think it's what's driving the initial growth of monkeypox, but it's also driving the fact that monkeypox is kind of crashing really, without having nearly as many cases as you would expect for a disease that initially grew as fast as it did. It's because these high degree individuals are getting infected, and then it's only now once they've been infected, they've recovered, there's really only low degree individuals left. It can still infect them, but it's just can't sustain itself nearly as well. All right. Yeah. So the key property, there's a key property that makes kind of the sort of mathematical approach I use work, which is that if you've got a node U and we've got 2 neighbors V and W, their statuses are going to be independent of one another. If I'm the only, in a configuration model network, if I'm the only, I have both of them as neighbors, but until I've had some influence on their statuses, there's no reason to expect them to be dependent on each other. There's no reason I can treat them as independent until I've affected their status. And then once I've affected their status, that tells you that I must be in the infected state, or SIR, I could be recovered. And then there's nothing that they can do to affect me. So until I've transmitted to one of them, their statuses are independent. Once I'm infected, I don't care about their statuses anymore. And only internal things can happen to me. So what that means is that basically when we build up a model, we can kind of assume that all my neighbors are independent until I'm infected. And then once I'm infected, I don't care about the fact that they get dependent on each other. And this is really important in configuration models. It helps us to write down some nice systems of equations. And it helps explain why this edge-based compartmental models that I've created works. But it also helps explain why people, when they use pair approximations, those approximations are actually correct in the large population limit rather than being an approximation in the large population limit. I would like to create clustered networks where this kind of property is close to right. So I want to introduce clustering. I want to maintain independence. This was published by Mark Newman in 2009 and by me in 2009. In fact, a week apart, we published basically the same paper. What I'm going to do is I'm going to create a clustered network. Now, when I say clustered networks, that means they're short cycles. Specifically here, I'm going to have triangles in my network. I'm going to create triangles in such a way that I've got two neighbors who can interact with each other. But if my neighbors V and W here interact with each other, they're going to interact with no other neighbors of mine. And that is going to build something that's kind of tree-like. So what I'm going to do is I'm going to do something kind of like a configuration model. I'm going to give people two different types of edge stubs. And I'm going to join one set into groups of three and the other set into pairs. We can also think about this as being kind of like a hypergraph. So a configuration model equivalent of a hypergraph that has edges and edges with three nodes would give you this. But we end up with a network that has triangles because we've got things joined into groups of three and regular edges, something like this. And in many ways, it's still very much like a tree-like network. You know, we've got branches. This branch doesn't interact with this branch. This branch doesn't interact with this branch. You know, the only way that I can have two nodes be correlated is if they are part of a triangle. And I will have to do more work to analyze the spreading process on these networks. But I can make good progress. I can still, I have to worry about how these two nodes are correlated when I think about what's going on with this central guy. But I don't need to worry. I can treat everybody else as independent of the correlations between these two nodes. I'm going to create a joint distribution of degrees. I've got an individual can have in pairs and in triangles. The key thing here is that we're generalizing configuration model networks in a way that allows us to introduce some clustering, but still be able to do some of the calculations that we know and love the configuration model for. All right, so I'm going to now build up the mathematical model, and I'm going to make two kind of axiomatic-like claims that let me sort of build a large population limit here. The fraction of the population with a given state should be equal to the probability a random node has that state. So if I'm in the case where I can do this law of large number sorts of thing, I can calculate the probability of something, and that gives me the proportion of the population that are in that state. So in a sense, this is very closely related to what Greg was talking about in the previous lecture. And if I alter a node so that I choose one node out there and I do something to it so that it cannot transmit after infection, this has no impact on its own state. Okay, so I'm in an SIR epidemic, and I'm going to choose one person in an SIR epidemic, and I'm going to say that person, randomly chosen from the population, is somehow unable to transmit to others because of an act of God. Can still get infected, still recovers under the same rules, but just for some strange reason cannot infect others. Then there is nothing about that random individual's status that is different from any other random individual status in the original population where he was able to transmit. And I'm going to call this individual a test node. And the status, if I can calculate the probability that this test node has a given status, given that the test node is randomly chosen from the population, that will give me the proportion of the population that has each status in my original population where I didn't have a specially behaving test node. And so calculating the probability my test node has a given status will give me the probabilities, the proportion of the population in my original world that has that given status. But because I prevented this individual from transmitting, I have independence of his neighbors. I don't have to worry about his status. The status of his status is independent of the status of his neighbors, or doesn't affect the status of his neighbors. So I can basically ignore him when I'm thinking about the status of his neighbors. All right, I'm going to do stuff in discrete time. And if I've got somebody who has degree K, and let me look at this for a moment. Yeah. I'm now thinking about the Watts threshold model where somebody can receive some number of transmissions over time. So I've got somebody with degree K. The probability that he has that this randomly chosen individual has received at least M transmissions, given degree K, is basically K choose M, where theta is the probability that a random neighbor has not yet transmitted to me. So in my SIR model, those of you who've seen what I did, I didn't need M to be bigger than 1, so I didn't get into all this. But now I'm in a case where I may require multiple transmissions before I change status. So I need to know what's the probability I've received at exactly M transmissions. Well, it's the probability that I looked at all my neighbors who haven't transmitted to me. There's theta to the K minus M, 1 minus theta to the M. If I've, yeah. I'm not doing that. Sorry, let me look at this for a moment. Yeah, yeah. So I've got K, I choose M of them, and I'm going to look at theta to the K minus M. Something's looking a little bit odd to me, but yeah, okay. The probability that I'm susceptible is then is the sum over all these things that is less than R. K choose M, theta to the K minus M, 1 minus theta to the M. Okay. So if my threshold is R, the probability I'm still susceptible is the probability I've received some number of transmissions less than my threshold. And now I'm going to just sort of sum these up over all the different possible states. I'm going to sum up the probability that I have degree K, the probability I have a threshold of R, the probability that I've received fewer than R transmissions, and then I'm going to sum that up over all of my different degrees. And then this will get me the probability a random node is susceptible at time t. There is a way to kind of express this big sum compactly in terms of a Taylor series or a truncated Taylor series. I don't want to go there. There's not much benefit to doing that. But if you've read my paper, or if you're looking at this and saying, why doesn't he do that kind of simplification? I'd like to just leave everything kind of explicitly expanded out here. Okay, so this is what this is, again, just to go through. I choose a random individual. The probability he's susceptible depends on his degree, his threshold, and then I look at the probability that he has a particular threshold and that degree. And then I look at the probability that he has received fewer than his threshold numbers of transmissions, and I add up everything. So, okay, I'm looking for S of t. I've now pushed this problem up into figuring out theta of t. So if I know theta of t, great. But I haven't told you that. But if I know theta of t, I know S of t. Theta of t, again, is the probability that a random neighbor of mine has not yet transmitted to me. So I have to figure that out. So to figure out the probability a random person is susceptible, we need to answer in terms of the probability a random neighbor hasn't transmitted. So if I know that, I can answer the question I actually care about. Okay, well, so I'm going to look at my random neighbor, and what's the probability? How do I think about my neighbor not transmitting to me? My neighbor hasn't transmitted to me yet, maybe because he's still susceptible. I'll call that phi s, or maybe he's infected, but he hasn't yet transmitted to me. And in the model that I've got, which is this discrete time that at each time step that person is going to transmit to me, if he is infected, then theta is phi s plus phi I, but my next theta is my current theta minus phi I. So if my neighbor is currently infected but hasn't yet transmitted to me, then at the next time step, my neighbor has transmitted to me, so that term there goes away. And I've got phi s. So I can figure out theta of t plus 1 in terms of phi s. Okay, so I want to know the probability I'm susceptible. I know that in terms of the probability my neighbor hasn't transmitted to me by time t, which I now know in terms of the probability my neighbor was still susceptible at time t minus 1. So we just need to work out probability my neighbor hasn't transmitted to me by time t minus 1. And I've got, I do exactly the same calculation, except that I don't worry for my neighbor, for Greg. You know, the probability Greg has passed on a rumor to me. I'm not interested in whether I fed that rumor to him and he passed it back to me. I'm ignoring that case. That would be more like an SIS kind of model, and those get horribly complicated and difficult. I'm only interested in Greg, whether Greg has transmitted to me because he learned about the rumor from someone else or some group of other people. So S of t is the probability I'm susceptible. Phi s is the probability that Greg is susceptible. Notice there's this minus 1 here because I'm not worrying about me transmitting to him. And notice that there's this scaling factor. I've got the probability Greg has degree k. Well, clearly Greg is somebody who I trust enough to care about the rumors he gives me. So he has at least one person who trusts him. So Greg has a degree at least 1. But in fact, you know, he probably has more friends than I do because he's my friend. So there's this factor here, the k divided by this angle brackets, I'm meaning the population average of k. So what magically comes out of this is that for Greg's probability being susceptible at the current time, I know that in terms of theta, which I've worked out how to figure out theta in terms of phi s. So I know theta phi s in terms of theta of t. I know theta of t in terms of phi s of t minus 1. So I now know phi s of t in terms of phi s of t minus 1, and therefore I've worked out all my thetas.
Why is there no binomial coefficient in the later expression?
Probably because of a typo. Yeah. So let's do that real quick. Okay, I think that's just a typo. Thank you. Yeah, it's exactly the same calculation. It's just that he's likely to have a higher degree k than me. So I've got to I've got to weight his probability of having degree k because of k, because his k is probably higher, and I don't care about me transmitting to him. So otherwise, it's exactly the same. Let me actually put that correction factor. I'm going to put that right here. So this guy here is the equivalent of P of K for Greg, accounting for him having higher degree with higher probability because he's my friend. And yeah, I need the K choose him. Thank you. Okay. All right. So what am I going to do? Well, first, for kind of SIR-like disease, these thresholds are geometric. I can come up with an SIR equivalent model if I make the thresholds distributed geometrically. I won't go into details of explaining that, but what ends up happening is that if I've got theta on my horizontal axis, theta of t plus 1 on my vertical axis, so a horizontal axis is theta of t, vertical axis is theta of t plus 1, then I've basically got a map that I'm going to think of as a cobweb diagram where I've got some function here, and I'm going to go from theta of t to theta of t plus 1 to theta of t plus 2, etc. And if I think about my initial infections, I'm going to assume are randomly distributed initially. So I start off with some random proportion of the population out there. Then it turns out that theta of t plus 1 is some function of theta of t, where that function happens to depend on rho. And I happen to have this property that f of 1 is equal to 1 minus rho. So I start off with theta of t. I have a random proportion of the population rho is infected. So at my very first time step with probability rho, I get a transmission from one of my random neighbors. Now, some of my neighbors may have just become infected. So at the next time step, I jump over here and I kind of step forward like a cobweb diagram, but I end up at this fixed point here. So this is what happens when you're kind of subcritical. You start off with an epidemic, you're subcritical. You get a little bit, if you infect a proportion rho of the population in a subcritical epidemic, it will grow a little bit. It's not going to go back to the original disease-free equilibrium where everybody's susceptible. It's going to go to a new equilibrium where a few people are infected and a few more than you started with, but it'll go to this fixed point. Or, if you have more people infected, it'll go to that fixed point. Or if you start off with more people infected, it'll end up at this fixed point. But it's doing something like this. That's if it turns out to be if the derivative here is less than 1. This happens, and that corresponds to R naught being less than 1. R naught greater than 1, this slope becomes positive, greater than 1. Same general kind of picture, but now what happens is we start off at theta equals 1. We go to here, we bounce down to here, we go over, we go over, we go over. Do I show that on the next slide? Yeah, so what happens here is that our cobweb diagram looks like that, and you end up at this fixed point way over here. Whereas in the case where R naught is less than 1, the cobweb diagram looks something like this, and you end up at the fixed point that's very close to no transmission. So you get two very different behaviors out of the configuration model network with an SIR epidemic. And even in the rho going to 0 limit, in the rho going to 0 limit here, basically nothing happens. In the rho going to 0 limit here, you still end up at this fixed point way down here. And you can see a little bit that the final size changes a little bit if you start off with a few more initial infections. This is what happens for some cases with the Watts threshold model. We no longer have the situation where right here, what's going on is these functions all have positive second derivative. So they're all kind of behaving like this. Basically, the derivative is changing monotonically. The Watts threshold model can do something different. You can have a picture where it comes up like this, it crosses the line y equals x, and then it crosses back again. In the limit where rho goes to 0, you still have to go through this point. but where you cross here, it's somewhere, it could be somewhere up here. But basically what happens as your initial proportion infected goes up, this moves down, and you can see that there's going to be a change in behavior. If you're below a threshold, you get something that looks like this, which is a lot like what you see for the SIR model subcritical. And what you see is that I as a function of time goes up a little bit, but it eventually is constant. So you start off, you increase a little bit, and then it's basically constant. At threshold, you get this picture. You start here, you bounce over, and you bounce over, and you start to approach this equilibrium, which is tangent. Notice this fixed point, it's tangent to this curve. And so what happens is it takes a very, very long time to approach that. And what tends to happen is you start off with some value of I, it increases a little bit quickly, and then it remains flat for a very long time. If you have a finite population where you're doing something stochastic, sometimes stochastic effects could make it jump across. If somebody has a slightly lower, you've chosen everybody's threshold from a distribution, but it turns out you got a few more people with a small threshold, and so it bounced across here. Or it was the way that the network was wired, the thresholds happened to be such that you had a few more people with a small threshold in one area. And if you can basically get past this fixed point, you do see this happen, where you got something where it's coming up, it seems to stabilize, and then stochastically it suddenly jumps up. The convergence, basically what happens, you get epsilon of t plus 1 is when you're close to this fixed point, epsilon of t plus 1 is epsilon of t plus something that is really, really small. Because, let me just leave it at that. Above the critical threshold, what happens is you get this picture. You get your opinion that's spreading, and it seems to be stabilizing. Nothing's happening, nothing's happening, nothing's happening. And then, it starts to grow again. And then it stabilizes again. So you can get these pictures where you've got something that starts, it grows for a little bit, and then it stops, or it seems to stop. It doesn't quite stop, and then it takes off again. And these are, think about this as an opinion. Once it's spreading, once it gets past some level, suddenly people start to believe it. Again, it might have initially been spreading through a group of people who are relatively ready to accept something. You've got a group of conspiracy theorists who are quite happy to believe that all mathematical modelers are lying. But if there's enough of them out there, it starts to spread to the conspiracy theorists. It's getting through them, and then suddenly it starts to become mainstream. And you can see this perhaps in the Republican Party. Well, I guess maybe I shouldn't do that. You can see this in some of the world right now, where there are people who, ideas that used to be very fringe ideas have become mainstream in some communities. So I guess, I would say you can see that in the Republican Party. I think it's probably fair that, other people might say something about that in the Democratic Party or in other groups. You can look at ideas that have been around for a long time, but are finally suddenly starting to become widespread. What happens here? If I just look at the final size as a proportion of the initial set of infections, if I look at how many people are initially seeded with this, when this picture emerges, what happens is if you start off with too small of a proportion with this idea, the idea just doesn't spread, doesn't get anywhere. If you start off with a larger proportion, it eventually gets bigger. If you start off really close to this threshold, what ends up happening is this basically is like a final size relation. It's looking sort of like a square root-ish behavior. It's becoming vertical at this point. And then once you get past that threshold, there's this discontinuous jump and you're somewhere off like this, and then it stabilizes, or it's getting close to infinite, close to everybody. So you get this very weird sort of transition here, where as you tune your control parameter, which in this case I've got to be the initial proportion who are infected, but you could imagine cases where your control parameter is the proportion of people who have a given threshold. It's some parameter of the threshold, the distribution of thresholds. You can get this very strange kind of jump. It's not a continuous thing like what you have in an SIR model, where you've got a epidemic dies out, and then suddenly once you pass the threshold, you get this big growth, but it's still a small at the threshold. Here, once you get past that threshold, there's a massive jump, and this is something that in opinion models is kind of concerning to me. I don't know whether that's necessarily a good thing or a bad thing.
I have a question there.
Yes, please.
So normally we saw yesterday some hysterics models and things like that, where actually phase transition looks very just, but it looks different. Whereas it doesn't diverge, and you could theoretically go along a metastable phase a little while. Whereas here you seem not to have that. So from the top, it looks as if maybe it looks like it could go into metastable thing and continue, but from the bottom, it seems to have infinite derivative. So so that's very atypical for first order phase transition. So what happens here?
What's happening here, fundamentally what's happening here is that there's some weird thing that's going on as we go through this sort of state. It's not so the picture that is happening with the SIR model is that basically as your R naught is changing, this initial slope is changing. And so when you start off with a very small number of infections, if R naught is less than 1, the slope at the endpoint is basically R naught. If R naught is less than 1, this crosses, and it crosses. It doesn't cross tangent or anything, it just crosses. And then as R naught gets close to 1, this is the point of this intersection starts to move really quickly. And so in the limit where rho, your initial proportion infected, is going to 0, in a sense, you don't care about the fact that slope is getting close to 1, because you're starting off so close to this fixed point that it still crosses very close. But once you jump past the slope of 1, you're no longer going to have an intercept very close here. The intercept is going to have to be way down here.
I understand.
Yep.
Sure.
Yeah.
And when you cross here, I understand this picture too. It's a standard first order phase transition.
Okay. Yep.
But what is strange is that at the boundary of your first order phase transition, usually you would get a second order phase transition.
Right.
But this thing is not a typical second order phase transition, because in addition to the divergence, you get a jump. So it's this that I don't understand. It's a very unusual. You don't see it in physics.
Yeah, it is very unusual. It can be understood, at least mathematically, through this picture that as it crosses, it's crossing tangent. It's tangent to the point where this cross happens. So basically, over in the SIR case, basically what's happening is that intersection moves to kind of when the slope is greater than 1, there's still an intercept, but it's out here at this greater than 1 case where I don't care about it. And you're going to another fixed point. Here, that fixed point is just vanishing. There's something sort of saddle notish kind of about this, where the fixed point that you're trying to converge to just disappears.
No, but I don't see it. So if I take your curves there and I move it slowly until it becomes tangent, right?
Yep.
The point where a tangent actually doesn't move discontinuously, that actually moves continuously and then jump. In your picture, you claim that the slope is
okay. So let's talk about that. That it is okay. So basically, as I increase rho, I slide down, this point moves a little bit. This point is moving as rho changes. If you think about this point as a function of rho, because these things are getting closer and closer to tangent, a small change in rho really is actually resulting in a larger and larger change in where this intercept is. So as I basically slide, if I took this picture and I slid it down, I started off here, up here, I slide it down, there's an intercept right at 1, it's moving, but as I slide it down, this function, the blue curve, is getting its tangent right at this point. So it really is moving very quickly. I can point you to where I've done the analysis on it, but fundamentally what it is, a small change in rho when this crosses transversely, when it just goes right across it, doesn't make a very big change. But if this thing were almost tangent, if this thing were basically almost tangent, that small change in rho, that small move of this function, you've got two lines that are almost tangent and you shift one of them a little bit, the place where they intersect moves a lot, potentially.
So let me formulate it different, not in physics language.
Yep.
When you have a mean field behavior which looks like that, typically fluctuations destroy that behavior.
Mm-hmm.
So I wonder whether that's an artifact of a mean field analysis and the real system behaves differently.
Okay, so if I do the simulations in the network, I do see that that close to that, I sometimes see one. Basically, what happens is when I'm close to that threshold, I get one of two outcomes. I can get an outcome where stochastically, I basically do get across this point, and I do get this sort of, it grows, and then it jumps, and then it grows again. But I can also get things that stochastically don't get to that point and stay a little bit below this line. So I do see in a large population, I never get a large, if I fix how far away I am from this threshold, so I'm not quite at the critical value, but very close to it, and I do a large enough population, then I do still get it behaves kind of deterministically. If I fix my population size, and I change my rho, what's going to happen is that I'm going to get to, once I get to some regime that's rho is close to my threshold, some of them are going to stay small and some of them are going to get big. And that's, I can't predict a priori which it's going to be. So basically I get two different behaviors can happen. But my final state here is sort of, it's, this is a monotonic, infections are increasing in this model. My final state is, has either a modest number of infections or almost everyone is infected, but I don't know which one it's going to be given my population size.
That's more in a thanks.
Could I just make a...
Mark Newman wants to make a comment here.
Yes, please.
Shall we microphone perhaps?
I think, in fact, this behavior is not unusual. This square root behavior is happening because you're driving the system all the way to the spinodal line where the bistability of the system disappears, where you don't have two competing equilibria anymore. And you actually see this in essentially any first order phase transition if you drive it all the way to the edge of the hysteretic regime. What we're seeing here is in the mean field class, as Christian pointed out. And so, for instance, you see this in the mean field treatment of the Ising model. You get exactly this kind of behavior where you get infinite gradient and then a jump. And as Christian also mentioned, the reason you don't see this in real systems is because of fluctuations that typically you get, before you get to the spinodal line, you get nucleation and the system will jump to the other equilibrium on its own. But in principle, in an infinite size system, you would see this infinite gradient. And you would see this, I think, in any first order phase transition if you treat it with mean field.
I think perhaps, here there's not quite the same sort of fluctuations that you have like with the Ising model. Once you go to I, you stay in I. If I had something where there was a little bit more, fluctuating back and forth, I think that would probably, I would end up somewhere very close to this threshold. And if there's fluctuations, I would eventually get past it, and I would take off again. But I don't know how, it could well take a very long time.
Carry on, Joel,
Yes.
and you have, just for your information,
Yep.
you have 5 more minutes.
Yeah, I am basically wrapping up. I'll say so the final outcome, so we can think about what this functional shape is. It depends on the distribution of the thresholds. It depends on the degree distribution. Typically, if you get a whole bunch of people who have a threshold of 1, you can get something kind of like this, where if you start with a larger and larger proportion infected, you get just kind of your normal final size sort of thing. Basically, if there's a lot of people whose threshold is 1, it takes off very easily. And there was a hypothesis in Watt's initial model that the only way you could start from sort of a rho equals 0 case. So right at rho equals 0, nothing happens. But at rho at all positive, you jump up here. So Duncan Watts made the prediction that, or a hypothesis, I guess, that the only way you could have a jump like this was if there was a lot of R equals 1 individuals in the population. Basically, that they are a giant component of the population. But I can go to clustered networks. I'm not going to go through all the details, but I can get to similar sets of equations. And I can get a case where basically I can get these sort of global cascades from rho being arbitrarily small, which can happen not if the threshold of 1 individual is sort of form a giant component within the population, but if you've got a case where you've got basically a triangle where you've got a lot of triangles out there where 1 individual has threshold 1 and somebody else has, and I have threshold 2. So if one neighbor has threshold 1, I have threshold 2, and my other neighbor, in this case, I've written it with threshold 1, but actually could have some other threshold, but node V forms the way that it gets into my triangle. W then magnifies them because W has threshold 1. Now my threshold of 2 means that I get infected as well. And if one of my other triangles has an individual threshold of 1 and threshold of 2, then it would immediately spread through that other triangle as well. So you can get this kind of, in a clustered network, you can actually get global cascades, even if rho is initially arbitrarily small. So your initial proportion that actually believes the rumor is arbitrarily small. If there are small cycles, they are small cliques or something where some of the individuals have a low threshold and they basically magnify it within my clique, and it gets into my clique from somewhere else, starts to spread in my clique, and I believe it because, well, there's a lot of my friends believe this, and it's just because my friends were gullible or had particular insight or whatever it is that's driving the opinion model to go. I think that's basically it. I want to give an advertisement for people who might have mathematical biology questions. I'm trying to create a repository so that we don't just teach mathematics through through physics examples. I'd like to start producing some disease and biology and health applications. There's a lot of them for mathematics, so I'm creating a repository of that. If anybody's interested in using or contributing to that, talk to me. My final kind of comments here. Look, for those of you who haven't seen Cobweb diagrams, I know many of you have. They're fun. There can be, for these complex contagions, there can be some really non-trivial interactions between complex contagions and the network structure. And you can get these really dramatic phase transitions to exist that are not the normal ones people talk about. And I think that's it. Yep. Thank you.
Thank you very much. There were several comments and questions during the presentation, as usual, which is nice. But are there more comments or questions?
Just, can you show again the previous slide?
Can you show the previous slide?
This one, the advertisement or the? Okay.
He's making notes on the link.
Okay, and I can share it as well. I can share the slides with you as well. You can email me. And I can definitely get you to that. At the moment, it's basically just a GitHub repository where I'm creating issues, which currently are mostly just reminders to myself of the idea, but I'll be expanding it out whenever there's not enough infectious disease that I have to spend all my time thinking about that.
This critical thing, I didn't quite understand. So rho was the fraction of initially.
Yeah, I'm starting off with some people initially infected, so to speak. So if I go to the,
Go back to where you saw the tangent thing. That was the one.
this,
Not that one.
So basically,
You had another slide where there was one curve and it was tangent. This one, yes.
Yep.
So what does this mean? Does it mean that if you start up here, maybe let's say this is 5% or whatever, you can get trapped at 10% or at 90%. Is that how I should?
Yeah. So basically, if I'm in a finite population and say rho is 5%, what happens is I start off, I'm a person in the population, 5% of the population's suddenly had this idea or gotten infected somehow. And so what happens is at the next time step, 5% of my neighbors have transmitted to me. So this is basically that theta variable. Okay, some of those people, once 5% have transmitted to them, some of them had a threshold of 1, some of them had a threshold of 2, and it just happened that 2 of their neighbors were initially infected. They became infected, and now they're going. So a small number of additional transmissions are going to happen from them, and it just keeps going. And and
does it mean that if you would simulate this thing 1,000 times, maybe some of these would stop here and some would stop here?
Yeah, if I'm in a finite population, some of them will basically get stuck somewhere around here. They won't hit exactly that point here because this is a deterministic assumption that's gone into it, but some of them will get stopped somewhere in here. And some of them, because of a little bit of noise, happen to get past here. And if they get past that, it takes off and it goes all the way to here. And so it looks a lot like this picture.
It's a repulsive fixed point, right? But very mildly, but not sort of this.
I didn't quite hear that.
It was a repulsive or unstable fixed point.
I want to be careful. So it's unstable from one. Yeah, it's unstable from one side. It's neutral. Well, it's neutrally stable. And if you go to the second order, the next order term, it's attracting from one side, unstable from the other side, and noise can get you past it. Okay. And if you're in a finite population, you may not quite get to it because it's finite. You can't get all the things stop.
Thank you, Joel. I think we reconvene at 2 p.m. Is that correct, or is it 1:30?
2.
So we reconvene at 2.
Okay.
Before we close this session, let's thank Joel once again.
Thanks. And I'm going to take another rapid test, and if it comes up negative, I think if there's no objections, I'll come in this afternoon. If you guys don't want me, but if my next test is also negative, I'll come.
All of us have R bigger than or equal to 2.
All right. Yeah. So I expect I'll be there for the afternoon. Just this morning I wanted to be sure. All right. Thanks, guys.